Okay, so looking at section 4.6 on our mean value theorem, we're going to start off with Rawls theorem. So if we look at Rawls, let's start off by looking at number 10. So on number 10, they define f of x equals 1 minus the absolute value of x, and then they tell us the interval from -1 to 1. So some of the things that we should be realizing on here is, first off, remember that Rawls theorem, we have to have something differentiable. So we have to have a continuous function. There also can be no corners or cusps that are going on within this. So if we think about this overall graph right here, we see that we're translated up 1 units. We have the absolute value with a negative in front. So we would see that we would have this graph right here. We're not differentiable at this corner right here, because once again the slope instantly changes from a positive 1 to a negative 1 right here. So it's not differentiable. So Rawls theorem does not apply right here. So we can't even do this problem because, once again, it's not differentiable. Okay, even though we are continuous, we're not differentiable on here. So it's always something we want to check before you start applying any theorem. Is remember those guidelines. Is it going to apply or not? Number 12. Number 12 says f of x equals x cubed minus 2x squared minus 8x. And which then we're on the interval from -2 to 4. So something to be thinking about on here is a simple fact that what we have going on is we have a polynomial graph. Polynomial graphs are continuous for all our points on here that we're going within. So, next thing, we're continuous. We're differentiable, because we just have basic curves going on here. So now for Rawls theorem, we're going to take a look at our endpoints. Okay, so we're going to take a look at f of -2, f of 4. So that means we're going to take a -2, plug it in here, type it in, and it equals 0. We're going to do the same thing for 4, so we're going to go 4 cubed minus 2 times 4 squared minus 8 times 4. And we see that this also gives us 0. Because our endpoints equal each other, now we can continue on with this. Because once again, Rawls theorem had a couple things that go into this. We have to have differentiable. So I'm just going to go yes, differentiable. I'm going to go yes, continuous. Once again, should be continuous before differentiable. And then as we look at the value itself, our endpoints are equal in each other. So now what this means is there should be at least one point that f prime of c equals 0. Okay, so if I go f prime of x equals, we have 3x minus 4x minus 8, and this equals 0. So what this is stating, that in this interval, because we have these values right here, x squared, we should have at least one value, one of our answers right here when this equals 0, should be in this interval somewhere. So we have to solve this. Well, it does not factor. So let's go to our quadratic formula. So x equals 4 plus or minus the square root of a -4 squared minus 4 times 3 times a -8 all over 2 times 3. So this equals, just kind of simplifying everything down. Once again, trying to save a little time, we got 2 plus or minus 2 root 7 all over 3. Okay, so if we were to simplify this down, and then we'd be able to cancel a 2 out of all 3 of our parts here. So now when we look at these values, because once again, I don't know what these values are. They look a little different in here. We see that we have 2.43 and then or negative 1.10. So noticing that we actually have both of our values happen to be in here. Now we knew we would have at least one of these would be in this interval. Okay, and that's what Rawls Theorem works towards. It's basically if we could find two values where we have the same overall value, so two inputs that give us the same overall, we know that there has to be at least one either local max or local minimum that is in between these values. In this case, we found two of them. So that kind of helps us with graphing purposes. It helps us business overall. When we look at this interval, we know, hey, okay, our answer has to be somewhere in between here. That negative on a business really isn't probably the best thing, but it's just one of those things that we start looking towards. Next thing we look at is the mean value theorem. Okay, so number 20. Okay, on number 20, here it asks us to compile a couple different components in here. It says determine whether the mean value theorem applies in the function in the given interval. If so, find the points that are guaranteed to exist by the mean value theorem. And then for those cases in which mean value theorem applies, make a sketch. We actually won't be doing the sketch part of this. We'll just be doing parts A and B. So we're given this overall function. F of x equals the natural log of 2x, and then we're on the interval from 1 to e. Okay, so on this interval from 1 to e, once again on our function, the natural log of 2x. So one of our checks right here is for the mean value theorem. If you look back, it says if f is continuous on the closed interval, in which then we are continuous, we plug 1 or any value in between here, we're going to be continuous. We're going to have this natural log curve that we're working with. So we are continuous. Remember, we can't have any zeros or negatives inside here, and neither of these are going to give us a 0 or a negative in. So we're continuous overall. And differentiable. Okay, so f of x is continuous. F of x then is, if we were to think about this overall, we would have some graph. If I go 1, and then here would be 2, here would be 3, so here would be e. We would have some graph happening, probably like this. Okay, if we're thinking that overall natural log curve that's happening. As we're considering that, as we're looking through it, we're seeing, hey, we just got this basic curve here. So we have no corners, we have no cusps, and we are continuous within here. We don't have any undefined that's going on. So yes, we're differentiable. Okay, so that's part A. So this is basically stating, can we apply this mean value theorem? Part B now. Part B actually asks us, if so, find the points that are generated. Okay, so remember on that mean value theorem, we're stating that f of b minus f of a over b minus a equals f prime of c. So, let's look at what we have here. Okay, I need another sheet of paper so at least I can kind of bounce back and forth into it. So if we look at what f of b is, okay, so f of b is going to equal f of e. Okay, once again, we're on the interval from 1 to e, and b is our second part here. Okay, so we're going to go f of e. So f of e equals the natural log of 2e. Okay, f of a, which would be f of 1 here in this case, because once again our interval is starting at 1, is going to equal the natural log of 2. So what we do now is we go to our formula, and we'll go the natural log of 2e minus the natural log of 2 over 2 minus 1, I'm sorry, e minus 1. E minus 1. So basically what I did was I took my formula and I found what f of b is, so that would be on my interval my e. So I plug e into my function here, and I see it's a natural log 2e. I plug 1 into here, and I see the natural log of 2 then. And then I'm going from e minus 1, once again the difference of our interval in here. So if we start simplifying this down, we see that this is the natural log of 2 plus the natural log of e minus the natural log of 2 over e minus 1. So we get 1 over e minus 1. So what this means now is that f prime of our constant is going to equal 1 over e minus 1. Okay? So we're going to have this right here is the value of the derivative at point C. So when looking at this, we know now that we have to have some sort of situation happening. We know that this situation that's happening here would have to kind of follow what the derivative is. So if we were to consider back to our original function, f of x equals a natural log of 2x. And then if we were to want to take the derivative of this, okay, one of the things to think about, this would be f of x equals a natural log of 2 plus the natural log of x. Okay, this is a constant. So when I take the derivative of this constant is going to drop off and become 0. The derivative of the natural log of x is 1 over x. So now f prime of c equals 1 over c. So I see right here that my mean value theorem stated that f prime of c is going to equal 1 over e minus 1. By taking the derivative of my original function, my derivative is 1 over x, so then when I evaluate my derivative at 1 over c, I get 1 over, or when I evaluate my derivative at c, I get 1 over c. So this means now 1 over c must equal 1 over e minus 1. Once again, c is our unknown constant that we're trying to find our value to be at, and then this is that numerical value that we worked with through the derivative. I can cross multiply. Either way, we get c equals e minus 1. So what we see here now is we see that basically from these two endpoints on this graph, so if I come back to my graph, from these two endpoints, if I have these two endpoints right here, we have some point right here where the slope is the same, and if I think about it, e minus 1 would be 1.72, so 1.7 about right here, so we're seeing 1 unit here, 0.72 here. We're seeing that, hey, at this point right here, we're sharing that same slope that the overall function had. And that's what this mean value theorem is really relating to and really starts getting into. Now, let's take a look at the application of the mean value theorem. Okay, for an application of the mean value theorem, we're going to be looking at problem number 32. Okay, problem number 32 has quite a bit going on with this. Now, we're going to be looking at parts A and B for this, but basically this is kind of how forecasters start working towards, because remember that mean value theorem tells us that there's at least one point on here. So avalanche forecasting. So an avalanche forecaster measures temperature gradient, d of t, d of h. So we're looking at the derivative of the temperature with respect to the depth that's going on. So, which is a rate at which the temperature in the snowpack T changes with respect to the depth h. A large temperature gradient may lead to a weak layer in the snowpack. When these weak layers collapse, avalanches occur. So basically what they're saying is that if we have this snowpack, so we have our overall mountain, and on this mountain we have our snow. Okay, if we go here to here and we see somewhere in here there is a huge change, okay, that means there's a weakness in here. and that weakness would have that collapse and then that avalanche that comes down. So they're trying to figure out, well, how do they go about this? So it says, when these weak layers collapse, avalanches occur. So avalanche forecasters use the following rule of thumb. If d of t with respect to h exceeds or is greater than 10 degrees Celsius per meter anywhere in the snowpack, conditions are favorable for a weak layer formation, and the risk of an avalanche increases. So we want to assume the following functions that go on. So an avalanche forecaster digs a snow pit and takes two temperature measurements. At the surface, h of 0, or h equals 0, so at our surface, h equals 0, we have negative 12 degrees Celsius. At 1.1, so at a depth of 1.1, we have a temperature of 2 degrees Celsius. We want to use the mean value theorem. What can we conclude about the temperature gradient? Okay, so what we're talking about here is we're talking about having this interval from 0 to 1.1. We want to look at what f of 0 equals and f of 1.1. Now do realize these do not have to be the same. That was Rawls Theorem. We're going to use our mean value theorem. So we got to consider what's happening overall. We have that negative 12 and we have that 2. Now do realize even though we're talking a depth, we would be going down. We're not doing that or not using it that way as a negative 1.1. That is part of the problem up here because that change in h was defined as a depth going in here. So that's why we're keeping these numbers being positive in here. So what we want to do now is we want to apply our mean value theorem. Okay, so that mean value theorem. The mean value theorem says that, well, f of 1.1 minus f of 0 over 1.1 minus 0 is going to equal f prime of c. Okay, so if we come through and we look at this, this would be a negative 12 minus 2 over 1.1 minus 0. Okay, so then we would simplify this, in which then we see we have a negative 12.7 degrees Celsius per meter, in which then we have to think about, we're talking about a change in here, so we will reference this then as 12.7 degrees Celsius per meter, once again because it's just an overall change that's happening, so we look for more towards that absolute value. On here now, is this formation a weak layer? Well, yeah, we're seeing that, hey, we're exceeding this 10 degrees Celsius per meter on here. 1 mile away, a skier finds a temperature depth of 1.4 to be a negative 2 and the surface to be negative 12. What can we conclude about the temperature gradient there? So once again, if we look at this other one, we're talking about h equals 0, so f of 0 equals negative 12, and then h equals 1.4, so we talk about this as 1.4 here, so we talk about that at negative 1. So rather than having a negative 12 to a 2, we're seeing a negative 12 to a negative 1. So what we conclude on here now is we could take, once again, our negative 1 minus negative 12 over 1.4 minus 0. Oh, I noticed right here I had these backwards. Yeah, so that would be why we should have a positive. This should have been 2 minus a negative 12. Sorry about that. So we see that we have our 12.7 on here. Just kind of looking back at that one, realizing that this went to the 2 right here, this went to that negative 12. So if we look here, we have that negative 12 going here, that negative 1. Simplifying this, going through, we see that we get 7.8 on this one. So once again, this one's not weak, so we see that a mile away we're okay, but in this area here, because it was at 12, we were having issues with it. So that's kind of the application overall. Once again, the mean value theorem takes a look at the function output minus another function output here divided by the difference in here. So we're looking at overall slope as being that derivative, because we know there's at least one point in here where we're having that drop going by this weakness, that 12. Here it's at a 7.8.